We describe our work on learning affinity via spatial propagation networks. Affinity describes the relationships between pairs of pixels or regions in an image. Natural images often contain strong pairwise relationships between pixels or regions. For example, spatially close regions are likely to be similar in color and texture. In the semantically labeled space, a pair of pixels that belong to the same class can be very far away in an image and not similar in appearance or texture. A typical CNN-based semantic segmentation algorithm uses a fully convolutional neural network to classify each pixel into semantic labels. However, it does not explicitly model the pairwise relationships between pixels. As a result, such strong pairs are not used effectively. In contrast, a well-learned affinity matrix, for example, by our proposed method, which is guided by the original image, can significantly improve details in image segmentation masks. It also incorporates contextual information since the affinity can describe semantic-level pairwise relationships. The proposed architecture contains two parts. The upper part is a propagation module that takes any coarse probability map as an input and outputs a refined result. The lower part is a guidance network that outputs the affinity matrix, which guides the propagation in the upper part. We propose a three-way connected module, namely the spatial propagation network. In the feature map to be propagated, the value of each pixel is linearly associated with three neighboring pixels in the previous row or column. The value is updated recursively from the first row or column to the last one. Since this module is differentiable, the whole network is trained end-to-end using an SGD solver. We theoretically prove that the linear propagation module with spatially varying transformation matrices is equivalent to a standard image diffusion model with a global and dense affinity matrix. And these matrices can be efficiently learned using a three-way connected structure. We use an independent guidance network to output all the scalar weights as the connections for each pixel. The three-way connection can formulate a triangular 2D plane in each direction, where the four directions result in dense connections of all pairs of pixels in an image. The SPN demonstrates significant improvement in accuracy for high-resolution face parsing and semantic segmentation. It quantitatively outperforms a dense CRF under the same settings with various baseline segmentation models. It is a nice alternative to graphical models used in deep learning tasks due to its significant improvement in accuracy and speed. For more details, please visit our poster.